Okay, welcome back to calculus. We're going to finish up our work in section 9.3 and chapter 9 in general by looking at a couple of mathematical models using differential equations to model something. One from population biology is called the logistic population model. It's a modification of the exponential population model. And then I want to show you something about some mixing problems that you might kind of see in a chemistry class where we're going to be mixing a couple of solutions together and trying to say something about the long run behavior of the solution. Okay, so maybe to motivate the logistic model, I can remind you that the exponential population model, exponential growth or decay, if something is shrinking. So the exponential model, I'm just going to be kind of brief about this. It says that the rate of change in the size of some population is proportional to the size of that population. All right. And if you solve that thing, it's a separable differential equation. Its general solution is something like a constant times e to the kt. So something is either growing or shrinking exponentially. And in the short run, for certain populations, that kind of makes sense. Like if you have, say, a petri dish of bacteria that's doubling in size every so often, then initially that petri dish's population size is going to grow exponentially. But in the long run, nutrients will start to be limited, right? Space, nutrients. So it's not realistic to think that this kind of growth will continue indefinitely, that there's some limiting factor on the population, that as we approach that limiting factor, the growth rate should start slowing down. And that's exactly the issue that the logistic equation tries to account for. All right, so it's a slight kind of just modification of the growth of the exponential growth model. So having said that, let's take a look at it. So here I have stated the logistic population model. I'm going to scroll that title off the screen there. You can read it if you can read my messy handwriting, but it's saying that the rate at which a population changes, so that's why it's a differential equation, it's proportional to not just the size of the population, like the exponential model, but it's proportional to the product of the size of the population and the difference between that size and some maximal sustainable size. Okay, that maximal sustainable size is called the carrying capacity. It looks like my eraser got a little out of control. Let me just write that again. The carrying capacity. So carrying capacity and maximal sustainable size are synonyms. So let's try to write this thing down as a differential equation. If we say denote T is time, okay, in whatever units, hours, years, it depends on the kind of population that you're studying. I'm just going to say T is time. And let's say Y of T is the population size. So it's the size of the population at time T. Okay, and let's give some variable. I'm going to use L for the carrying capacity. So it's some quantity, it's a constant that's given, right? But we'd have to estimate it with statistical analysis if we were out actually studying a particular population. So what does this thing say? It says that the change in the population size, that is the derivative of y with respect to time, is proportional to, so it's some constant times, well, the product of y and the difference of y and the population size. That's y, but the carrying capacity, excuse me. So it's the product of y and y minus L. So this is the logistic model written down as a differential equation. And that differential equation is separable. Yeah, if I divide both sides by y times y minus L, multiply both sides by dt. It's a separable differential equation, which we will solve by integrating both sides. Yeah, the integral of the right-hand side, of course, is just kt plus some constant. And the integral of the left-hand side is going to require some partial fraction expansion, right? Because I want to integrate something that looks like 1 over y times y minus L. So as some side work over here, I'm going to do my partial fraction expansion, I think, over here on the right-hand side of the screen. So what am I trying to do? I'm trying to write 1 over y times y minus L as some number over y plus some number over y minus L. So clearing the fractions gives me that equation. And then if I, let's say, y equals 0, y equals 0 tells me that a is minus 1 over L. Yeah, if I let y equal L, the equation tells me that B is equal to positive 1 over L. All right, so if I factor that 1 over L out, then I would have 1 over L times the quantity of, well, it would be the integral of negative 1 over y. My a was over the y term, dy, plus the integral of 1 over y minus L, okay, dy. Right-hand side, we've already integrated, kt plus c. Okay, so if we multiply both sides by L and do those integrals, we get what? Minus log absolute y plus the log of the absolute of y minus L is equal to LKT plus LC. And I'm going to pull some kind of common shenanigans in differential equationville here. I'm going to rewrite this left-hand side using log properties. So it's the natural log of y minus L over y. And on the right-hand side, this is going to look a little funky. I'm just going to write kt plus c. So you might be wondering like, hey, I thought it was LKT and LC. Well, I'm just renaming the constants. I'm not trying to keep track of everything in terms of those original constant names. You can if you want to, but the idea is that some initial conditions and data points determine these constants, and I don't really care if the constant was L times some other constant. So it's just sort of notationally simpler. So if that bothers you, then what you should kind of do is say, okay, well, let's call this K1 and C1, and then write down K1 is L times K, C1 is L times C. But I'm just saying that's kind of unnecessarily complicated. I don't really care. It's renaming them. But it can be algebraically a little bit confusing. I hope it's not troubling to you. Okay, so now I want to try to solve this thing for y. So usual idea, we exponentiate. Y minus L over y is e to the kt plus c, which I'm going to write as e to the kt times e to the c. And I'm going to pull those shenanigans again. I'm just going to rename e to the c, c. Yeah, so I'm not ever trying to keep track of things in terms of the original constant. So if I were, I'd be on my third one here now. C2 is equal to e to the C1, and C1 was equal to L times C. But I'm just going to reabsorb it every time it's a constant. Okay, and for that matter, because C is a constant, I could absorb a sign. I'm going to ditch these absolute value signs over here. Right, so if C has to be negative, then so be it. So I can kind of absorb the plus or minus by ditching those absolute values into my constant. And now I just have to solve this thing for y. So let me just do the algebra. I'm going to multiply both sides by y. Then I'm going to subtract, put my y terms on one side, non-y terms on the other, factor out y. Oops. It's y times the quantity 1 minus c times e to the kt. And if I divide both sides by that parenthesized expression, I've got the solution that I'm after. Y is equal to L, the carrying capacity, over 1 minus some constant, which I'm calling C, times e to some constant, which is called k, times t. But be careful, that k, it's not the original k. The original k in the model, the constant of proportionality, is this new k is actually L times it. But we don't have to worry about that in practice, because if we were given some initial conditions, if we were given, let's say, y of 0 was some value, the initial population size, that will determine the value of C. I'm not going to do it in a specific example here. I'm just talking about the nature of the model. But yeah, if you plug in t equals 0 into this expression, well, e to the 0 is 1, so you'll determine that value of C. Right? In fact, I mean, you can do the algebra if you want and write it in there in terms of y0 and L, but I'm just going to leave it kind of vague like this. And then if I knew some other value, if I knew at some time, say t1, the population size at that time, well, that would determine k. All right, so you'd need these two pieces of information to determine those two constants in the formula. Cool. So that's the solution to the logistic equation. And what I wanted to do is just sort of look at some pictures of this thing. I've got a Mathematica notebook set up. I'm going to switch my sharing window. So what are you looking at here? You're looking at the solution, y equals L divided by 1 minus C times e to the kt, but I can just change L and C and K. Yeah, the parameter that we understand the best is the L, the carrying capacity. So it's the y coordinate of that orange line in the picture. And you can see that no matter what I make L, right, for fixed C and K, the shape of the curve, this is the size of the population, it's approaching that carrying capacity as time goes on. So you can kind of see this population starts off growing exponentially. It's got that kind of exponential bending up shape, but then somewhere it kind of starts slowing down. Its growth rate becomes closer and closer to zero. So the population approaches that carrying capacity. So I'm just kind of giving you a physical intuition of what the carrying capacity means in the picture. It's the limiting value of the population. It's an equilibrium in our previous terminology. If we looked at a direction field for the logistic equation, then we would see that y equals L is an attracting equilibrium in that direction field. So you can say, well, what does C and K do? On the screen before I said, well, if you put in an initial condition, it determines C. So C is kind of related to, it's not equal to, but it's related to the initial condition. So notice that the population's initial size over here changes when I change C. Yeah, I can even make the initial size bigger than the carrying capacity. And look, the model says, oh, if that's the case, then the population's going to want to shrink. So for this population, what have I got L set to? 67. Let's just make it something round, like 70. So if this population starts off with more than 70 individuals, it wants to shrink towards 70. If it starts off with less than 70 individuals, it wants to grow towards 70. Okay, that's kind of cool. And then what does the K do? The K is kind of a relative growth rate. So it's going to affect how quickly the population grows. Yeah, so this population grows quite quickly in the beginning. It approaches its carrying capacity quite quickly as I make K bigger. You can see the ranges if you want to on my Ks. And then, yeah, if K is smaller, the population grows less quickly. But so these are kind of cool curves because it's exponential growth in the beginning, but then it starts to taper off, and it tapers off because of that second factor. When we put in that factor y minus L in our differential equation, we got this kind of more realistic version of how a population grows, because it grows when resources are abundant and time is small, things are growing exponentially. But sooner or later, we start running out of resources, running out of space, and so our growth rate slows down and we'll approach some limiting factor, some carrying capacity. Okay, so that's what I wanted to tell you guys about the logistic model. Let's switch back. Again, I'm not going to do a specific example with an L and a K and so on, but if you want to come to the office hour, we can certainly do something like that. But I want to switch back now to the whiteboard screen and talk about a mixing problem. Okay, so I'm going to just use a book problem to illustrate this idea. So I'll let you check out this example. You can stop the video and just read it yourself, but I'll kind of narrate it in case you want to hear me do it. But I've got a tank, and a tank, it starts off with 20 gallons, or excuse me, 20 kilograms of salt dissolved in 5,000 liters of water. And then brine, which is just a salt solution, which contains 0.3 kilograms of salt per liter. So that's a concentration. Yeah, it enters the tank at a constant rate of 25 liters a minute. We mix the solution thoroughly. So that just means that assume that the density, the concentration of the salt is constant throughout the solution. And then we're draining the tank at the same rate. So the tank always has 5,000 liters of solution in it, right? Because we're coming in at 25 liters a minute, we're going out at 25 liters a minute. The fluid level in the tank is never going to change. And the question is, how much salt is in the tank after a half an hour? All right. So let's let T be, say, time in minutes. It's in minutes because we were given rates like 25 liters a minute and so on. And then let me just give a name. I'm going to be boring and call it Y of T. This is the amount of salt at time T. That's in kilograms. Okay, so what am I trying to do? I want to find Y of 30. Right? It's asking me how much salt is in this tank after a half an hour. Find Y of 30. Well, I can find Y of 30 if I can find Y. So here's the basic idea of a mixing problem. The differential equation the change in the amount of salt with respect to time, well, there's sort of two reasons the salt is changing. There's salt coming in, right? Because we have 0.03 kilograms of salt per liter, and it's coming in at 25 liters a minute, and there's salt going out. And that difference should be the change in the salt, right? Because the salt's either changing because it's coming in, that's why it has the sign plus. It's changing because it's going out, it has the sign minus. So this is the basic principle of the model, is that the rate of change of the salt in this tank is the change of it coming in minus the change of it going out. And we have all of that information, right? The salt is coming in at 0.03. I'm going to put the units in here, kilograms per minute. And that's doing that at 25, excuse me, 0.03 kilograms per liter. I'm talking too fast. 0.03 kilograms per liter. And it's coming in at 25 liters per minute. So I can see right away, that's the right units. That's kilograms per minute. That should be the units on this. Y is in kilograms, time is in minutes, dy dt is kilograms per minute. What about the rate out? Well, it's also leaving at 25 liters per minute. But what's the concentration of the salt leaving? Well, it's changing in time. There's Y kilograms of salt in there at time t, but there's always 5,000 liters of solution in the tank. So Y over 5,000 is the concentration at time t, yeah, in kilograms per liter. And so again, the liters cancel, so that's also in kilograms per minute. So if I just clean this up and drop the units from the notation, our differential equation is that dy dt is equal to 0.03 times 25 is 0.75. And then 25 over 5,000 is 1 over 200. So that's y over 200. This would be in kilograms per minute. That's our differential equation. What's our initial condition? We were told that at the beginning, this tank has 20 kilograms of salt in it. Okay, so this is our initial value problem that we need to solve. We've got a differential equation and an initial condition. Cool. You can rewrite this thing getting a common denominator. You can write this as 150 minus y over 200. And I'm going to do that so that when I separate this equation, I've got a fraction. So I've got dy over 150 minus y is 1 over 200 dt. And I'm going to integrate both sides of that. Left-hand side with respect to y, right-hand side with respect to t. So the integral of the left-hand side is minus the natural log of 150 minus y. The right-hand side would be 1 over 200t plus a constant. And then exponentiate. Well, actually, let me multiply by minus 1 here real quick to isolate my log. So I've got log of 150 minus y is minus 1 over 200t. Same shenanigans. Instead of minus c, I'm just going to write plus it. It's just some constant. And I'm going to anti-differentiate both sides. Or excuse me, exponentiate both sides. So I get the absolute value of 150 minus y is e to the minus t over 200 times e to the c, which you know me, I'm just going to rename that c. Constant shenanigans and differential equations. I can absorb the plus or minus sign into the c by, so when I write these absolute, I'm just going to ditch them. So I've got 150 minus y is c times e to the minus t over 200. Okay, in this form, we can find our initial condition. If we use the initial condition, remember when you plug in t equals 0, we were supposed to get 20 for y. Well, 150 minus 20 is 130. E to the 0 is 1, so c is 130. And then if I just rewrite that, solving for y, we've got our solution. Y is equal to what? 150 would be minus 130 e to the negative t over 200. So that function gives me the amount of salt in kilograms in this tank at time t. So if you wanted to know how much was in there after 30 minutes, you'd plug in 30 I'll let you do the calculator work yourself, but plugging in 30 in there, you should get about 38.1 kilograms. So that's how much salt is in the tank after that. Okay, and then let's end by just looking at this graph. You can see in our solution, if you let t go to infinity of our solution up there, well, the decaying exponential term is going to go to 0, so we end up getting 150. Yeah, we end up getting 150 kilograms of salt in the long run. And if you look back at our concentration, remember it was coming in at 0.03 kilograms per liter. If you multiply 0.03 by 5,000, I think you're also going to get 150. And that makes sense to me because in the long run, this well-mixed solution should basically be what the concentration of the salt is that's coming in. All right, cool. Well, I mean, what I just said was a little bit dimensionally incorrect. If you take 0.03 kilograms per liter and you multiply it by 5,000 liters, you'll get 150 kilograms. And that makes sense because that's kind of the long run concentration of this tank. In the long run, the concentration in the tank should be like the concentration of the inflow. Okay, so I hope you thought that was fun and interesting. Thanks for listening.